Hello everyone, welcome to my presentation. I'm Xingbo Wang, currently a postdoc at the Medical School of Cornell University. The paper I will present is CommonsenseVIS, visualizing and understanding common sense reasoning capabilities of natural language models. Common sense knowledge describes general facts and beliefs about the world that are obvious and intuitive to most humans. For example, my parents are older than me and take an umbrella when it rains. It can be generally represented as graphs, where nodes denote the conceptual entities and links describe the relations between different concepts. For example, rain causes wetness, which can be protected by umbrella. Equipping machines with human-like common sense reasoning abilities is a long-standing challenging topic in NLP. Researchers have constructed common sense QA benchmarks for developing natural language models such that they can benefit various applications in our daily life, such as social robots. Current language models with billions of parameters achieve impressive results on common sense benchmarks. However, they lack interpretability and transparency, which hinders model debugging, development, and deployment. NLP experts do not know if large language models know properties of a concept, or they merely explore superior correlation in datasets. Essentially, the question is, what common sense knowledge language models have learned and used in the reasoning process? To understand the NLP model's reasoning process, feature attribution methods such as SHARP can quantify the importance of input features, for example, words and phrases to the model outputs. Therefore, NLP experts can identify critical concepts for model predictions and determine whether they are aligned with human knowledge. However, these methods cannot reveal models' relational reasoning over concepts in different contexts, since common sense knowledge is implicit and not included in the model input. However, context may influence the reasoning over relations between concepts. Furthermore, feature attributions often focus on individual instances, given the complexity and vastness of the common sense knowledge space the models operate on, where concepts such as office are intertwined with various relations and contexts. It is challenging to scale up this method to efficiently build high-level abstractions of model behavior. To solve these limitations, we employ a knowledge graph to derive implicit common sense in QA instances as context. Then we use it to align model behavior with human reasoning through multi-level interactive visualizations. Thereafter, users can understand, diagnose, and edit specific knowledge areas where models do not perform well. Here we showcase our system by using ConceptNet to contextualize model behavior on concepts and relations in CommonSense QA dataset, which contains multiple choice questions. Each question contextualizes relations between a question concept and a target concept that is the correct answer. Triplet of these concepts and relations are drawn from ConceptNet. First, our system CommonsenseVIS takes in QA instances and an NLP model to compute model answers. Then it extracts the reasoning passes with ConceptNet concepts and relations to connect the question concept and the target concept. This pass helps align the model behavior with ConceptNet. Meanwhile, it identifies important concept that is words in the questions using feature attribution methods. We align the model behavior with ConceptNet knowledge regarding different concepts and relations. For concept alignment, we found those large positive influences on the model predictions as model concepts. Then we compare the differences between them and the ConceptNet concepts. For relation alignment, we surface the model learning of their relations by investigating the relationships of model inputs and outputs. Specifically, we calculate the translation matrix from the question stem embeddings to the answer embeddings. If the two are close to each other after transformation, the model could possibly learn the relations. Next, we present multi-level visualizations to guide the exploration of model behavior on different concepts and relations. Moreover, The system supports model probing and editing for improvement on targeted knowledge area. The model exploration process starts with the global view, which summarizes model performance on different concepts and relations and assesses the overall relation learning. The global view adopts different projection strategies and group question stamps and target concepts according to different criteria. For example, we use UMAP projection with relation types as supervision signals to form clear separation between relations. Users can then filter out interested relations by clicking the corresponding green bars in the middle. Meanwhile, the correspondence between question stamps and target concepts reflect the overall relation learning. And they can apply correctness coloring to diagnose and select the error instances. After selecting a group of interested instances in the global view, the subset view summarizes the concepts considered important by models in varying contexts, aligning them with the extracted concept net concepts. This view employs cluster glyphs to analyze model behavior across instances with semantically similar question concepts, question stamps, and target concepts. For each cluster glyph, two bars at top show the average accuracy and overlap ratio between model concepts and concept net concepts. The lower part displays the differences between the model and concept net concepts. The first row displays the top concept net concepts frequently missed by the model, and an orange bar is put to the left, revealing the frequency. Then the second row shows the frequent model concepts and their frequency with blue bars. Finally, the instance view provides statistics and local explanations about the model. For individual instances, users can edit them to form and validate hypotheses about the model learning of relations. Users can bookmark instances about specific knowledge that the model does not learn well. Then they can conduct model editing in the model editing panel to make localized updates. Specifically, for model editing, we train neural networks to modify original model parameters that can correct the model answers and their semantical equivalence without affecting unrelated knowledge much. For example, when asking about the current US president, we can correct the model result to Joe Biden. However, we do not want to modify other unrelated knowledge, such as who is the president of France. Now, I will introduce a case study to demonstrate how CommonsenseVIS helps users diagnose an open source general QA model, Unified QA v2, on the validation set of CSQA dataset. In this case, the expert wanted to know under what situations the model may fail to use context for relational reasoning over concepts. He first clicked the first green bar in the middle to filter out the largest relation group at the location, and he found good correspondence between question stem and the question concept clusters under the relation transform projection scheme. It implies good learning of ad location in general. The expert wondered when the model might fail to reason about context. Then he noticed that a group of dense red bars appear at the bottom left. The accuracy of this group is low, and the expert decided to lasso the group for further exploration. In subset view, the expert noticed that question stems fall into three clusters with varied accuracies, as suggested by the green bars. Particularly, he was interested in the leftmost cluster since it has the lowest accuracy yet a similar high question stem hit ratio compared to the other two. As he hovered over the cluster glyph, he discovered that the top model concepts are not so meaningful. He speculated that the model frequently relies on superficial information in question stems for answering the questions. After clicking the cluster glyph, the expert explored incorrect instances in the instance view. He found several interesting cases where context associated with movie. For example, in one question, he found that although air conditioning can also locate at movie theater, the model ignores the important context, watch the game, which normally happens in the house. Then, He further modified this instance to verify his finding, specifically through several edits around watches in the original question. The model still chooses movie theater, even though these contents, such as television or live shows, usually do not happen at movie theater. Therefore, the expert thought the model attaches superficial information of watch to movie and does not understand the context. The expert then located the related instances by searching keywords movie in the search input of instance field. He added those incorrect instances for model editing in the model editing panel. Finally, he saw that editing accuracy is 100%, and the model maintains nearly the same performance as the original version. In summary, we contextualize model behavior with the external knowledge graph to achieve human-AI alignment. It features an exploration, explanation, editing, post-hoc model analysis workflow. Here, since ConceptNet is large and comprehensive and CSQA is built upon ConceptNet, it is reasonable and sufficient to use ConceptNet to cover the Commonsense knowledge in CSQA. In the future, we can increase the coverage of different types of Commonsense by integrating other knowledge graphs and knowledge representations such as arithmetic and logical operations. CommonsenseVIS also has some limitations. For example, to assess the overall relation learning, we apply the translation to the input embedding and align it with the output embedding. However, it is also possible that the question and target concepts are connected through nonlinear transformation. Moreover, the model behavior probing can sometimes lead to incorrect model understanding, and we can improve the system design to handle more complex questions with multiple plausible answers and explanations, those often influenced by diverse arguments and opinions. That is all, thank you. Welcome to check out project page and my homepage for more details.